Okay, so we are going to look at daily practice two-dimensional motion problem B, and it reads, a snowboarder traveling 3 meters per second flies horizontally off the edge of a jump. The jump is 8 meters high. How far from the base of the jump does the snowboarder land? Okay, so let's examine our object. What object are we interested in exploring the motion of? And that is that snowboarder. Okay, now we want to define when the motion starts that we care about and when the motion ends that we care about. So we're interested in when that snowboarder goes off of the ramp or the jump, and then when he lands in the snow. There's our initial and final. When we start that stopwatch, when we end that stopwatch. All right, so time to define the world. So here's our snowboarder. These are crazy hats. And there's the jump. So he's going to go off the jump. We need to define both the both the origin in the horizontal and the origin in the vertical. So the horizontal origin defines the world between rights and lefts. So if we divide the world in half to the right and left, we might say that the origin is there at the end of the jump, or to the right is positive. Of course, to the left are negative locations in space horizontally. So we want to make sure that we define that as the horizontal origin. We also have to decide on the vertical origin, what divides the world vertically, both up and down. So if we set our vertical origin equal to 0 at the ramp, the height of that jump, then above that value and below that identifies our positive and our negative locations in space in the vertical direction. So 2 dimensions, 2 origins, right? So identifying this as a 2-dimensional problem. So then we want to list our knowns both in the horizontal. So we have initial horizontal position, final horizontal position, initial horizontal velocity, final horizontal velocity, acceleration in the horizontal, and time. And we don't identify time horizontally, of course, because time horizontally and time vertically match each other. In the vertical dimension, we'll have those same players. It's always the same players. So our initial vertical position, final vertical position, our initial vertical velocity, final vertical velocity, our vertical acceleration, and our time. All right, so again, I encourage you to pause, fill those lists in, and then make a double check, and we'll look at the list together. All right, so initial position in the horizontal direction. We've defined the location at the end of the jump, when I care, as being location 0. So horizontally, we start at 0. The final position is where he's going to hit the snow, somewhere out here. And we aren't exactly sure what that will look like. So our horizontal final position is unknown. He's flying off the ramp purely horizontally, so he does have a horizontal velocity, and we're told that that is 3 meters per second. Now, as I've drawn it, he's going to be traveling in that direction, so indeed that's a positive, and then we have our positive 3 meters per second. Final horizontal velocity. Well, we want to keep in mind that in the horizontal direction, there's no change in motion. And so our acceleration horizontally, nothing's influencing it. Gravity, remember, only acts vertically. So free fall is only vertical. So we have no acceleration. If we have no acceleration, then we have no change in horizontal velocity. And so our final horizontal velocity should match that initial velocity. Time. It's not given in the problem. It remains an unknown. All right, that's our list for horizontal. What about the vertical motion? Again, we can do this because of that independence. Horizontal motion, totally independent from vertical motion. Very, very powerful. So our initial position vertically, well, I've defined the origin in the vertical dimension at the level of the jump. So our initial position vertically is 0. It tells us that the jump is 8 meters high. So when we get to the ground again, we know we're at a position of minus 8 meters in the vertical dimension because it's 8 meters below the origin. So our final lands in the snow vertically is 8 meters below the origin. The problem states we're moving purely horizontally when we leave the jump. And so if we're purely horizontal, we have no motion in the vertical dimension to begin with. But of course we start to free fall. We're not sure how fast we're going when we land in the snow, but we do know in the case of free fall, our acceleration is negative 9.8 meters per second squared. That's that gravity value. And again, we don't know the time. So the question is asking how far from the base of the cliff, how far in this dimension does the skier land, the snowboarder land? Well, that's a relationship horizontally. We're interested in the final horizontal position. So if we look at that equation, the one that gives us final position information, we know that x final is equal to the initial position plus the initial velocity times the time plus 1/2 the acceleration times the time squared. Now this is going to be of interest in the horizontal dimension. So let's put in our variables. Our final horizontal position, we don't know, so that remains a variable. Our initial horizontal position is 0. Our initial horizontal velocity is 3. We don't know our time, plus 1/2 0 times our time squared. As usual, anything that's multiplied by 0 is just going to go away. And if I simplify this equation, I end up realizing that I need time. Okay, well, time then becomes a variable of interest. Time is now something I care about. I have the opportunity in both the horizontal and the vertical dimension to get time. I only have one other relationship related to velocity. And so in the horizontal direction, I know my position equation isn't going to give me the time information that I need because my two velocities are the same. The velocity relationship is not going to help me either. So I can look in the vertical dimension. So if I want to be interested in time, remember time's in both. But I have more information in that position equation. So let's just remind ourselves again that the position final is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And now we're interested in the vertical dimension. So x final is negative 8. X initial is 0. My initial vertical velocity is 0 times my time plus 1/2 negative 9.8 times my time squared. All right, anything related to or multiplied by 0 is going to give me 0. And I end up with negative 8 equals minus 4.9 times time squared. And doing my algebra, I will end up with a time equal to 1.28 seconds. So my time is now a value that I know. I've been able to calculate it, and I can now use it where I need to. So going back to my final position, which is what I wanted, x final is equal to 3 times my value of time of 1.28, and I find that x final is equal to 3.83 meters. Now we want to make sure that that answer makes sense. Values again are a little bit tricky, but we certainly can examine the direction. Should my final position be to the right of my origin? And indeed it is. And if I'm going 3 meters per second and I travel for at least a second, I'm going to at least go 3 meters. And so it's reasonable to have a position that's beyond that 3 meters. So again, two-dimensional motion, everything just sort of got doubled. I still identify my object. I still pay attention to what's important. When do I start? When do I end? Defining the world requires two worlds, a vertical dimension and a horizontal dimension. So once I have that definition, I can look at my motion independent in the horizontal from the vertical, total independence in horizontal and vertical motion. I still go after what I'm interested in. This answers the question. And when I go after that, I realize what I need. What I need might be related to the other dimension. I can go after that in the other dimension and use that information. Good job.